So I'd like to welcome you to today's GOC technical session, where we will be discussing how to set up the GOC as a CC-Link I-Field Basic Master, as well as a Modbus TCP Master to control a E800 Ethernet VSD, or two separate VSDs in this case. So just to start off, as we have covered in previous sessions, the GOC43 has built-in Ethernet port, which not only facilitates your programming of the GOC, but also opens the door to Ethernet communication to field devices, which we have mentioned for the GOC is the CC-Link I-Field Basic Communication Protocol and the Modbus TCP Communication Protocol. Now, the Ethernet port allows for up to 8 simultaneous connections, so you're able to add up to 8 devices on the Ethernet port. For your CC-Link I-Field Basic protocol, the GOC can only be configured as a master, whereas for your Modbus TCP protocol, it can be configured both as a master or a slave. Both of these communication protocols can be configured on the GOC simultaneously, which in turn means that we are able to communicate to different field devices using both of these communication protocols simultaneously. So the objective for this presentation or webinar is to discuss how to configure our GOC43 as both the CC-Link I-Field Basic and Modbus TCP Master in order to control two E800 VSDs simultaneously. And the functionality we would like to bring to controlling the VSD is to run forward and reverse, stop the VSD, reset. So for the run high, middle, or low speed, I will be leaving that out for today, just to try and keep to the time frame we have available. But all of the information is in the presentation, which I will be providing to you afterward. So yeah, we will be skipping that one bullet point for today. So after reset, we'll be doing set a run frequency, and we'll also add monitoring our output frequency of each of the VSDs to the functionality. So with that in mind, let's start off with the CC-Link I-Field Basic protocol and configuration. So, as we noted, the GOC can only be configured as the master for this protocol and not as a slave. And another thing to note about the Modbus the CC-Link I-Field Basic Communication Protocol or configuration is that it only allows up to 4 connections on this specific communication protocol. This still leaves you with 4 other connections out of the maximum 8, which you can use to connect to Modbus devices, TCP devices, or you can configure an FTP server on the GOC. So if you're not too familiar with CC-Link I-Field Basic, this is a Mitsubishi Electric developed protocol, so it's specific for the Mitsubishi PLCs and so forth. And this communication protocol transfers data cyclically. And when it comes to the mapping of the data transferred, or the, in this case, the what is referred to as link IO, it is as follows. There are 64 input bits, 64 output bits, 32 read words, and 32 write words that are transferred between the CC-Link I-Field Basic Master and slave station. Now, this IO or data transferred, it cannot be changed by the user. This is determined by the communication protocol. And each slave device will have its own IO table for what is being transferred, which we will be covering for the VSDs today. One thing to note as well, for the GOC, these link IO variables are addressed by the user. So the addressing of these variables are defined by the user, which is different to the Modbus TCP protocol, as we will be discussing in a bit later on, where that is automatically assigned within a specific memory area of the GOC. So when it comes to configuring the GOC as a Modbus CC-Link I field basic master, it uses a function block to do this. So by executing a specific function block within the application protocol, the GOC is configured as a CC-Link I field basic master. Now, this function block can be found in a Mitsubishi Electric library, namely the GOC43 underscore CCB library. Now, to find this is automatically included within the GOC toolkit. So when you download the GOC toolkit of Codesys, this will be included. There's documentation available to explain how this library or function block works. And to find the documentation, you can look in your GOC toolkit folder, which you can see here. And when you go to your manuals and then library manuals, you should see a document saying GOC43 CCB library manual. And this specific manual will look something as follows. So you'll see the function block and it explains to you what the different input parameters and output parameters of this configuration function block is. So I'll be switching a bit between Codesys and the presentation today. So to start off, I've already created a project with some few things included, such as variables and POUs, just to try and make or fit today's presentation into the time frame we have. So what I do have or have done already is set up my communication to my GOC and just set up my PLC settings. So to start off with importing our or the function block or library, you'd open the library manager from the device tree, right click anywhere, which opens this add library window. Then you'd select advanced and expand miscellaneous in the next pop-up window. You'll see the GOC43 underscore CCB. That's the library we require, and select that and say OK, and it should now be added to my library manager. So doing this will allow me to go to my programming area and drop in a box and then browse in that specific function block I'm looking for. So to do this, you just select the question marks within the box itself and use the action button to browse in the function block. So it would be under the function blocks tab, and you can see the library that was imported, and it is this specific function block. So you'll also need to give your function block an instance name. So if you can see, this is the function block that is used to configure my GOC as a CC-Link I field basic master. Now just quickly switching back to the presentation. Let's take a look at what the how to configure the input as well as the outputs of this function block. So first off, your first input is the run input. This is a Boolean. This allows you to activate or start your communication as a master. So you start the communication of the GOC as a master, and it will then communicate with the slave stations. When this bit is false, so when this input is false, communication will be stopped to all of your stations. And just as a note, you only require one function block, even though you have multiple slave stations. So you only require one. So all 4 of your slave stations, or the max 4 of your slave stations, are configured and communicated with through this function block. So here's just an example of the program part. So turning on the run, or the run of the function block. Next off is the number of stations. So this is a byte type variable, and this basically just stores the amount of stations you want to communicate with. So basically the amount of stations you have connected. This should not exceed 4, as I mentioned previously. 4 is your maximum amount of stations you can connect. So this will just, for our demonstration, be 1 station. Next is the CC-Link iField basic station list input. So what this input does, it kind of points to the address of an array, which stores information like the station number, as well as the number of occupied stations of each slave. So one important thing to note for this one is when it comes to the station number of a slave, the GOC uses the 4th octet of your station IP address. So to give you an example, if my VSD IP address is 192.168.3.9, this will mean my VSD station number is equal to 9, and you would set it up like that. So just an example of the variable declaration for this input. You can see at the bottom here where this is where we only are configuring one slave station, so there's only one station defined, and the station number, as I mentioned, is 9, and we are only occupying one station. So this will change if you have more stations, and it will look like what you see in the area that is commented out. So next, the timeout period, which is a word variable. This just stores the time timeout period for when a retry for a retry response. So it basically times how long it's trying to communicate, and whether, depending on how you set up some of the other inputs, whether it should stop trying to communicate or do another retry. Your timeout period can be set, or is set, in milliseconds, and your range is 1,000 to 65,535 milliseconds. And it's quite simple to declare this variable, an example of which you can see right here. So this is set to 1,500 milliseconds for the demonstration. Next is the counts. This is where you set the number of retries you want the GOC to do when you have lost communication with a slave station. So you can either set this as 3, 5, or 10. The reset diagnosis, this basically just decides what action is taken when the communication is reset or retried. So when you set this at 0, no reset action is taken. When set at 1, reset output parameters like your max link scan time and your minimum link scan time. 2, it clears the latest error code if cause for error is corrected. So if you have fixed the error, it will clear the error. And 3 is a combination of the previous 2, and anything else than this, so anything more than 3, no action will be taken. So the next few inputs is where we declare what addresses our link IO or our data transferred between the master and the slave will be stored. As I mentioned, this is done by your user. This is user defined, and you can define this within your marker or marker memory area, which is denoted by the %M. So you set each you need to set each of these link IO types. So RX, RY, RWR, and RWW each need to have a separate and unique starting address, and you need to keep in mind that this is only the starting address. So if the next starting address is put too close to the previous one, it might overwrite some variables. So to keep in mind, when you have one station, once again, RX, RY all require 64 bits, which in this case is compiled into 8 bytes. RWR and RWW require 32 words. Yeah, so that is what you need to keep in mind when declaring these starting addresses for your link IO. Now, obviously, the more stations you have, the more space you require for each of these. So if you have 2 stations, you'll require 128 bits for RX and RY, and 192 for 3 stations, and 256 for 4, and so on and so forth. Note also, when you do this input, you use the ADR operator. This is also true for whenever you see a PTR. So for the CC-Link iField Basic Station List and the next one we will do, you'll require the ADR operator as a way to point to that variable. So the slave station info actually stores information of each of your slave stations in an array, and each array position is a struct. So this contains communication information, vendor information, as well as some error codes, which you can use to troubleshoot when you're having trouble communicating with one of your slave stations. So just to give you a bit of a breakdown, this is part of what is available within this variable. So you have vendor code, model code, device version, station error code, dealing status, so you can see what is happening with your slave station. You also have the following: a communication error code, so it shows you whether there's duplicate IP addresses or no response from a slave station, and so on and so forth. You have transmission status, disconnections, and a retry counter as well. So yeah, this variable is very useful for troubleshooting at the end of the day. Now, to go to the output side of things, your first output is your done, which is a Boolean type variable, and this just indicates whether the configuration was done successfully or not. Next is your error underscore com. This holds a error code in the case that there was an error with the configuration or communication. And when the error code is 0, it means there's no error. When it's 1, one or more connected slave stations are not communicating. And 2, there are multiple stations. There are multiple master stations on one network. For the error config, this holds the input parameter configuration error code. So if there is a problem with any of the inputs you have set up, this will give you an indication what that error is. So 0 is no error, 1, station number is invalid, 2, address overlap error, so that means that one of these starting devices is overlapping with the previous one. 3, number of slave stations or number of occupied stations is out of range. So that would be, let's say, if you set up 5 slave stations, so that would be out of range of the 4 maximum. Same station number configured for more than one slave is when your error code is 4. When your error code is 5, it means your master station IP address matches one of your slave stations. So that means your IP address for your master and IP address for one of your slaves is identical. Error code 8, it's the count value is set to anything else than 3, 5, and 10. So if you do recall, you are only able to set 3, 5, and 10 for your retry count. So that's the counts one here. And 10 indicates that master function block is already configured. So that means that you've most likely added 2 configurations or 2 of these function blocks, and you are only able to add 1 because you can only configure the GOC as the master once. Now for your max link scan time, as well as your minimum link scan time, this stores the maximum and minimum value of link scan time. So basically how long the communication cycle takes. And then your current link scan time is just your current one. So your maximum gives you the largest recorded one, or the maximum recorded one, and the minimum recorded one of the past, where your current is your current cyclic transmission time. Now, when you have declared all these variables for your function block, it will look something like this. I can actually show you this on Codesys itself because I've already added the variables beforehand. So to start configuring, we'll start off with our inputs. So for the run, we'll be adding a bit of a delay to allow the GOC to start up before configuring it as a master and initiating the communication. Otherwise, the slave station might not be able to communicate to the GOC. So we'll just give it a quick delay as follows. So we'll set it as master config delay. And we'll say this needs to start when from the very first scan, which to do that was always on, which is sysvol CPU. And if we look at our system bits and bit 0, apologies, bit 0. So that will start off immediately when my GOC goes into run mode. And I'll just set this to 10 milliseconds. So this allows me to just delay that start of the master configuration slightly. Okay, so now when 10 milliseconds has elapsed, the master configuration will start and the GOC will initiate communication. So next up is our station number. of number of stations, which I have set up as number of stations right here. So I'll just copy and paste it. So our number of stations for this demonstration is 1, because we only will have one VSD that is communicating over CC-Link I-Field Basic. Next, we have our station list. Now, once again, this is the first or the one of those that need to be or are of type pointer. So I need to point to this address, and then I'll just use the variable that I've set up. So just to show you, my VSD is set up as 192.168.3.9. So this means that the station number for this VSD will be 9, which I have set up right there. And the number of occupied stations is equal to 1 as well. Next is the timeout period, which I've also declared right here. And I'll just enter that. So I've set it up to be 1.5 seconds before a retry needs to be attempted. My number of retries variable goes next for counts. And then reset master diagnosis is the next. So this determines what action is taken for a retry or a reset. Now, this is once again where you need to use the ADR operator for our link IO starting addresses. So my starting addresses are in the marker memory, 3000 for RX, 4000 for RY, 5000 for RWR, and 6000 for RWW. Sorry, that is incorrect, and this is correct as well. And for the last one, so that is the starting addresses for all the link IO that will be transferred between the master and the slave, which in this case is our GSC and a VSD. Last but not least, we also have the slave info. So this is also a pointer which you require the ADR operator for. And I've set this up as this variable. So the size of this variable or array is dependent on the amount of slave stations you have. So if you see, I only have an array with one position. So if I have 2 slave stations for the CC-Link I-Field Basic Protocol, I would change this 0 to 1. Or if I have 3, I'd change it to 2, which allows for 3 positions in the array. So that is also something that needs to be kept in mind when having more than one station. And for the outputs, it's fairly straightforward. It's just adding the variables, that's the wrong one, to the outputs, like so. You also have the option of not adding variables. Let's say to some of these, it will actually not give an error if you do this, and will also save some space within your GOC's memory. So I will now bold just to check that I have no errors for this. Okay, it doesn't like that. Okay, so it accidentally copied the colon. So let's just replace this and build again and see if it now comes back without an error. Okay. So now it compiles without an error, so it seems like the function block is satisfied with the variables I have provided for the inputs and outputs. So this is the function block for configuring your GOC as the CC-Link iField basic master, and this is how you set it up. So if you see, it looks similar to what you see here. Now, apart from setting up the GOC as the master, you'll also be required to set up your slave station, which for this case is the E800 VSD. Now, the parameters you see in this table is what is required for a CC-Link iField basic slave station configuration on the E800 VSD. But note, this is only the parameters required for the communication part of it. You still need to set up your basic parameters like your motor nameplate details within your parameters, or just in general, you need to set up your parameters according to the application you are using the VSD for. Some additional parameters that are also related to CC-Link iField Basic but are not necessarily critical is parameter 77, which is your parameter right selection. If you want to be able to write parameters from your GOC to the VSD via CC-Link iField Basic, you will have to set this parameter to 2. Next is the Ethernet communication network number, and this is mainly required when you have more than one network. And last but not least, the station number. Now, this is a bit of a unique case because for the GOC43, we know that the station number is the last digits of your IP address. So the station number actually doesn't apply for the GOC43, but in any other scenario where you are using another master station other than the GOC, you will most likely need to set this one up. So if you recall, I've been referring to link IO and RX, RY, and so on and so forth. So the VSD gives you a detailed explanation on what the different what the data is that is transferred between the GOC or whatever master station it is connected to, and this is the RY signals. So your RY is your output bits. So this is commands and so on that you are sending from your master station to your VSD. And this includes your forward rotation command, your reverse rotation command, your high, low, and middle speed commands, and so on. This is also what we will be using to control our VSD. The RX, it's input signals or input bits. So this is signals that the VSD that is being read from the VSD to the master, and this gives the master some feedback of the VSD status or even operation. So for instance, it can give you feedback on whether the VSD is running forward, reverse, whether it's up to frequency, whether there is an error. So you also have error status flag and so on. Your RWW is your remote registers that are written from your master to the VSD. And this is used to set frequency, select what values you want to be monitored, and so on and so forth. Your RWR, these are remote registers that are once again read from the VSD to the master, and this also gives some feedback. So this can give you fault codes or fault history, and you can monitor values of the VSD through these variables. So our configuration for CC-Link iField Basic is completed. So now we can start moving on to programming the control of the VSD. Apologies. So to start off, we'll start with the start forward or reverse and stop for the VSD. So just to give a quick, go back quickly. Our start forward and start reverse are RY0 and RY1 respectively. When neither of these bits are on, this acts as a stop command. So to stop the VSD, we need to turn off both these bits. And the VSD will also not move when neither of these bits are on. So yeah, you'll always be required to turn on one of these. Now, just as a quick indication, if you look at the variables that I have declared here, you'll see I've already declared the RY0 and set the address according to what it would be due to the configuration. So if you recall, I've set up RY starting address as 40,000. Now, RY0 is the first bit, so the first address for that range. So it starts with 40,000.0 because this is a bit, and the declaration is in byte form. So that is 8 bits. Yeah. So this means that our start forward and start reverse are bit 0 and bit 1 of register 4000 respectively, and we'll be using these variables that are declared here in our program. So to start off, we'll start by just saying this is VSD1, which I will be referring to the VSD that we are controlling via CC-Link iField Basic as VSD1, and the VSD that we are controlling via Modbus TCP as VSD2. Start and stop commands. And we'll start off with this. So I've also set up some variables that act as my HMI buttons to kind of ease the control of the VSD and allow me to do a few more things within the program. But you are also able to directly browse in these link IO variables, so those that you're directly reading from the VSD into your visualization objects. So I would like my start button apologies, it's froze. Okay, sorry, I'm not sure what that was. So I'd like to have my start button, and stop button. Like so. And then I would like to be able to select whether I want to start forward or start reverse. So to do that, I'll add another negated contact. And I've created a variable, a Boolean variable that toggles forward and reverse selection. So when this bit is 0, it is in forward, and when this bit is in reverse, is 1, it is in reverse. The VSD will run reverse. So when this is negated, I want to activate, or when this bit is 0, I want to activate the run forward command. So I have set that up, or that is RY's 0. So I'll just look for the variable that I've set up for this, which is this one. So RY0, which is 40,000 bit 0. And now I add a branch, and I just use an normally open contact. And when the bit is on, I would like the VSD to run in reverse. So that is how I will be, or how we will be toggling between forward and reverse rotation. And that is function-wise, that is all you need. But one thing to note, for the HMI, we will be toggling the start and stop push button. So I will need to reset the HMI bits, so the input bits right here, when when the other is pressed. So to do this, we'll do the following. So just as a bit of a trick, with the way the Codesys environment works, you're only allowed to add one connection to your rail on the left-hand side in any network. So I can't add another connection to my rail within this first network. So to do this, I'm using the always on bit to allow me to do 2 branches to reset each of my HMI bits. So first off, let's start with when my start button is pressed, I want the stop bit to reset. So when this is pressed, I would like a reset coil. So reset of my stop. And basically just repeat that, but for the stop. just remember to convert this to reset. So now when start is pressed, the stop will be reset and vice versa. Okay, so the next thing we'll be looking at is the reset. So we'll reset of the VSD. So this is the reset command. And if you take a look at our table, the reset command of the VSD is RY1A. And yeah, you'll have to work out what address this will be if you want to create a label or if you in general just want to use this. But for our demonstration or for this case, this is equal to bit 40,000 or register or address 40,003, and it is bit 2 of this register. So this is what we will be using. This variable is what we will be using to send the command to the VSD. So to do this, we'll be using another delay. So you want your command signal, so the RY18, to be on for at least 50 milliseconds, so that your VSD resets, and then you need to reset this bit. So to do this, we'll once again be starting off with the always on bit to allow me to branch off, after which we'll be browsing in our HMI button to activate the reset, as we are not using the link IO command but directly. So we'll be using this time off, and this is a reset. This is to turn our reset flag off. So we would like the time to be 50 milliseconds. I do not require the elapsed time for anything. So, and I would like to negate this input, because that is how this block works. And then once the time has elapsed, we would like this bit. So when this bit goes on, or this bit needs to stay on for 50 milliseconds, so we would like it to activate the command bit, which is RY1A. I might have scrolled past it there. Okay, so we want this bit to turn on for 50 milliseconds to reset our VSD. And once the 50 milliseconds have elapsed, we would like to reset our HMI bit, so that it will, otherwise the VSD will actually just continuously reset as long as that bit is on. So that's incorrect. I would like the so this is the output coil of this function block. So when this turns off, I would like to reset my bit, this one. So this is how you would use the reset command for the VSD. Obviously, there are quite a few ways to do all of this. This is just how we will be doing it for this demonstration. So now we are able to start forward, start reverse, and reset, or stop and reset our VSD. But we require a speed reference for our VSD for it to actually start working. Otherwise, telling it to start forward, it will not do anything because it doesn't know what speed to run at. So for today, and we will be using a set frequency, so where the user is able to define a specific frequency for the VSD to run at. You also have the choice of using your run high, medium, or middle and low command bits, which if I just take a quick look at the table, your high, middle, and low speed is RY2, 3, and 4. And when one of these bits are on, they will run at that speed. But for this demonstration, we'll be specifically using the set frequency. So this will actually use quite a few, like two link IO. The first being RW1, so this is a register, and specifically the lower 8 bits of this register is used to set frequency, as you can see here. Now, this is just where you store the value that your VSD needs to run at. So for instance, if I want the VSD to run at 50 Hertz, I would store that value in this register. To actually execute the command to run at this frequency, you are required to turn on bit RYD or RYE. Now, using bit RYD will write your frequency to the RAM of the VSD, whereas turning on bit RYE will write the frequency to both the RAM and the EEPROM of your VSD. It is not recommended to write to your EEPROM if the frequency is going to be changed quite frequently, because your EEPROM obviously has limited reads and writes. So for this demonstration, we will be using RYD to set the frequency. Just another note on the value. So as I mentioned, RWW1 will contain the value of the frequency that you want the VSD to run at, but the value for this is scaled by a factor of 100. So easiest way to explain it, if I want the VSD to run at 50 Hertz, I am required to put the value as 5,000 for this register for the VSD to run at 50 Hertz. So you need to always factor it by, or scale it by 100. And this kind of leaves space for you to allow decimals. So I can set decimals for this. So if I say 50 Hertz 0.12 or 12, this will be 5012. So it allows me to set decimals without using a real data type, so the real value, which makes the communication a bit more efficient. So you will always have to keep this in mind when setting a frequency. And this actually also applies to when monitoring the frequency, but we'll get to that in a moment. So to start off with the programming, let's create a new network. And we'll once again start off with just a always on bit, because this will not execute unless my RYD is on. And as I mentioned, you kind of need to scale your value. So if the user inputs the value as 50 Hertz, I need to scale it by 100. but you can also allow the user to add decimal values, which in this case I have. And the register I'm using on my HMI side is this one, which is set up as a real to allow the user to do the decimals. So I will be required to 1, multiply by 100, and 2, convert from real to word, because the link IO is of type word. So starting off with the multiplication or the scaling. So the user inputs it into that variable via my HMI. And I've set up a temporary variable sorry, that's 100. I've set up a temporary variable just to store the in-between value before it is input into the uh, link IO variable. So this is just this one. Oh, come on. Okay, it doesn't want me to copy and paste. I'll just okay, it's that variable. Then, as I said, I need to convert this now to a word, which I do as follows. So to convert from real to word, I use a conversion block like this, and I want it to convert to word. So I just select to word, and I say I want to convert it from a real. So it's this variable I want to convert from real to word, and I'll store the converted value directly into RWW1, which is this one for the set frequency. Okay. Now, having done this, you have set your value, the value is set in the correct register, and now you need to activate the bit to actually have the VSD run at the speed. So to do this, we'll add another branch. And add a coil. And this needs to be RYD because we are writing to our RAM. So this will be the set frequency command in the RAM. I can also just add that I don't want this to write unless start is on, although this is slightly redundant. So that is how you would set the frequency for your VSD via the application program. And next, we have now set the VSD frequency, but we can also monitor the actual output frequency of the VSD. To do this, we will be using 3 of the link IO variables. The first being the monitor code. So how the CC-Link iField Basic protocol works, you have multiple monitor code variables, which you basically set up what values you want to monitor. So as you can see, we have monitor code 1, 2, 3, 4, 5, and 6. So for this demonstration, we will be using monitor code 1. So this will be applicable to the lower 8 bits of the monitor code will be set in the lower 8 bits of this register RWW0. Now, apart from your monitor code, you also have your instructions. So setting the monitor code doesn't automatically mean your master is going to monitor the VSD for that specific value you want to monitor. You also need to give it the instruction to monitor, which is RYC, your monitor command. So to monitor, you need to activate this bit. And last but not least, you've now told the VSD what value you want to, or what you want to monitor, and you've given it the instruction to execute. But where is the value you monitoring stored? This is in your RWR, so the read registers. And where that value is stored will be dependent on what monitor code you used. So as I mentioned, for this one, we will be using the first monitor code, and therefore it will be stored in the first monitor value register. So if you do it in the third monitor code, it will be stored in the third monitor value, and so on and so forth. Okay, so to start off, we have a new network. Say we want to monitor our output frequency. Okay. So we will always want to monitor the output frequency, so we can just use a always on bit, which is this one. And then to set the monitor code for the output frequency, there is a separate table indicating the monitor codes, which if you scroll down, you'll see the monitor code table. So we are monitoring output frequency in the lower 8 bits, so we need to set hex 01 in our monitor code register. So this means using the move function, I will set the value 1 in hexadecimal, although it doesn't really matter in this case because it is only 1. And this will be moved to my monitor code register, which is RWW0, monitor code 1 and 2, because it's set in the lower, this will be set in the lower 8 bits. So for instance, if I wanted to set anything if I wanted to set it in the upper 8 bits, I just add 2 zeros at the back of it. But because I want to set it in the lower, I'll just put 0, 1. So that is how you set up your monitor code. Now next, like I said, we need to instruct the VSD to actually execute this, so to actually monitor, because now it knows what we want to monitor, but it doesn't know to monitor yet. So to do this, I need to turn on bit RYC. So monitor command. Now the VSD will monitor. If you recall, I mentioned that the output frequency when monitoring this, it's similar to when you set the frequency in the way that you need to actually scale the value. So once again, the value that you receive from the VSD, let's say your VSD is running at 50 Hertz, will be 5,000. So that's what you will monitor if your VSD is running at 50 Hertz. So for display, you will need to, once again, scale it appropriately. So to do this for our application, I will kind of be doing the reverse of what we did for setting the frequency. I will be converting the value from a word to a real, and then I'll be dividing it by 100 so it does not lose any decimals. So I also have set up a temporary variable for this, for also the in between the conversions and calculations. But first, we want to convert, apologies, this needs to be the other way around. So we are converting in this instance from a real to a word, which the word would be the link IO of the data that is transferred between the master and the VSD, the GSC and the VSD. So this would be RWR0 because we are monitoring in the first monitor code. So this would be the first monitor value, and we'd store that in our temporary variable, which is this one. Next, we would like to divide it by 100 as to scale it appropriately. And this is the value that you would like to divide. And I've also set up a variable for display, which is right here. So this would display my scaled output frequency. That is all the programming side of things we'll be doing for that is actually then incorrect. Sorry. My apologies. That needs to be custom frequency. Apologies. Just as a separate note, yeah, this is all. Okay, so let's start. This is all that's required programming wise for our scope specifically. But as a separate note, you can set up some of your input variables to retain. So in this case, I've set up my custom or the frequency set by the user to be retained so that it's not lost during a power cycle. So the set point for the frequency will actually always be retained within the GOC memory. This just helps with not having to set up this set point every time the power cycles for the GOC. Now, when it comes to the HMI side of things, it's quite simple. We'll just be setting up some visualization objects as buttons and as displays to allow you to control your VSD via your HMI and to monitor the values you want to monitor. So starting with our start button, if you see I've already started setting up one. So this is actually a shape visualization object. So this is actually a normal rectangle, which you can also set up as a button. And my reasoning for using this instead of an actual button is I'm able to control the colors or the background colors of this shape when the bit is active. So I can customize this by setting a color in my alarm state and then adding the variable that I want to toggle this color for in color variables toggle color in the properties window. So I'll be looking at my start push button variable. So this will be the same variable that is toggled when this is pressed, and to configure what action needs to be taken when this visualization object is pressed is the input configuration and click or use an appropriate one. So I'll be using on mouse click, so this action will be taken when the button is pressed, anytime the button is pressed as well. So to do this, toggle variable, and just add what variable needs to be toggled. And now that's my start button set up. So for ease of use or just speed, I'll just be copy and pasting and changing this to my stop button. And I'd like this to display red when I press it, and obviously the variables used for the color and the variable toggled needs to be changed as well. So in this case, this is the stop push button, which is this one. So that is my stop button. You can do the same for your reset. I'll keep it red for the reset as well. And I'll just change the variable that controls the color, and once again the variable that is toggled. Okay. Oh, and just change the text as well. Just to check that we aren't running into any errors, I will quickly just do a bold. Okay, so that compiled without any errors, so we can go on. Next, to set our frequency, we can also use a shape, but for this, we can specify that this needs to be, or so we specify a placeholder to indicate where the variable will display firstly, because you would like to see what value you actually set. And if you recall, the input variable that I have set up is of type float, so this will be F, the placeholder will be F, and the .2 just indicates that it displays up to 2 decimal points. So this will now be able, or is starting to set up for displaying what frequency the user has set, but you will need to add the variable that needs to be displayed in the text variables, text variable field, which in this case is my custom frequency variable. I'm also able to, if I'd like, it says set frequency, that, and we'll still display it there. Now, when this visualization object is clicked, I no longer wanted to actually toggle a variable. In this case, I actually wanted to write a variable. So let's change this to the write variable. I want to use a specific variable, which for this is this one. And I can add a minimum of maximum and minimum for the user input so that they don't go out of range and enter, let's say, ridiculous variables or values for this variable, and say okay. So now that is set up to actually allow the user to enter a value there. And last but not least, let's monitor the output frequency. So this is slightly simpler because you just need to set up the display part that we set up for the set frequency. So I can actually remove this configuration right here. So I no longer want this to write a variable. And the value that we want to display is the scaled output frequency for VSD1, which is this variable right there. So that is the HMI part of the first VSD. So I'm going to rebuild or build, compile, check for errors, and then I'll load this onto the GOC so that I can show you how it operates. Okay. Once the GOC is ready, I will start the run. Okay, so it's just asking me to rescan my network. So it might have been a disconnection issue. So let's try again. Okay, much better. I can actually see it starting to download to the GOC now. Okay, I actually left out one thing in terms of the HMI controls. So apologies, let's go back. To select whether you go forward or reverse, uh, I'll be adding a simple dip switch. So this you can find under lamps, switches, and bitmaps. And the visualization object looks something like this. And all you really need to do is add in the variable that you'd like to toggle. In this case, it's the forward and reverse rotation selection. And just as a note, in the presentation, I also show you how to display forward or reverse to see which way this variable is toggled. So if you'd like to take a look at it, you are most welcome to do after today's session when I have shared the presentation with you. So that is all that is required for the forward and reverse rotation. So apologies, but yeah, we'll have to download once again. Just because I see we are a bit um, delayed on time, or this is taking a bit long, let's start looking at our Modbus side of things. So just a quick check. Okay, it's almost finished. So I'll just give you a quick start with the Modbus. So Going back to the introduction, our GOC can also be configured as a Modbus TCP master, and for this you can add up to 8 slaves, as opposed to the CC-Link iField Basics maximum 4. And this is also limited in the fact that if you have any other connections other than Modbus per se, you will have to keep in mind that your maximum Modbus connections is also determined by the other communication protocol connections you have. So yeah, you can add up to 8 slave devices on the Modbus TCP master or configuration, but this is when no other connections are made. For the IO mapping for the Modbus protocol, this is done automatically, so it's automatically generated by your configuration of the GOC, and this will automatically be given an address in your communication protocol interface memory area, which spans from input word 32 to input word 2047, and output word 32 to output word 2047. Now, this means that you have 1008 words for inputs and outputs respectively for the Modbus TCP communication protocol. However, this memory area is shared by both Modbus TCP and Modbus serial, and this is applicable whether the GOC is master or slave in both of these communication protocols. So you need to keep in mind that you only have this amount of memory area for all of these communication protocols and configurations. So to see how the memory is mapped, so your read coils or read discrete inputs digitals is stored in the input bits range, read holding registers, input words, write coils, output bits, write holding registers, output words, and read write holding registers is also done in your output words. I'm sure the program has finished downloading, so I'll just quickly jump back so that I can just demonstrate how the program functions. Okay, so you can see currently my VSD is not commanded to start or stop. So let's start by adding a frequency set point. So I will be doing this on the HMI, but you can monitor my ladder code so you can see what is happening. So on the HMI, I am setting 50 Hertz as the frequency, and you can see the value set in the link IO is 5000. So when I press start, my VSD will now start running. I'm not sure if you can hear the motor as well through my mic. And here you can see the speed of my VSD changing as we are monitoring it. Now, as you see, the selection bit is in forward rotation, so it's off, so it's selecting forward rotation. And if I select my dip switch, you'll see it change, and you'll also see the speed of the VSD decreasing, and then once again ramping up in the other direction. As you can see, it's starting to ramp up now. And there it has reached its 50 Hertz. And when I press the stop button, you'll see the start resetting, and the VSD will now start stopping. And that is all the functionality that we've added. Obviously, for the reset command, you need to be in a reset or fault state, but I can show you just by pressing it. It happens fairly quickly, though. You can see the action in the ladder program. So that's just how the CC-Link I field basic VSD is controlled. Let's continue with the Modbus side of things. So, contrary to how the CC-Link I field basic communication protocol is configured, where the GOC is configured as master, these Modbus is actually done through settings, which let's actually go through this. So same program. I want to add the Modbus TCP master configuration. To do this in your device tree, you right click on Ethernet, then select add device. So what you want to do now is expand miscellaneous in the add device window. Not miscellaneous field buses, and then select Modbus master, this device. So to do this, or doing this, you'll be setting up the GOC as a Modbus TCP master. So when you select add device, it should now be added under Ethernet in your device tree. So when you open up Modbus TCP master from your device tree, you now see you are able to set some things up, including your response time and your socket timer. It actually does nothing, but you can also select whether it should auto reconnect or not. You can also see some IAC objects and so on. Generally, there's not much you set up for your master configuration. The thing that you need to do though is add slaves underneath your master. So this is just setting up your GOC as the master. I need to now add slave connections. So to do this, once again, go to Ethernet, right click on Modbus TCP master and select add device. Now you will have one option, which is to add a Modbus TCP slave. Do so by selecting and adding device. And now the Modbus TCP slave will appear underneath the Modbus TCP master. So you can also configure this by double clicking on it in the device tree. And here you set up your IP address, your response timeout, and your port. So my slave device IP, so the IP for my VSD is as follows: 192.168.3.10. And we keep the port on 502 because that is standard for Modbus. So this is the configuration for your slave device. There's a bit more that you need to do in this window, but that comes more when you are actually programming your the GOC to control or speak to the Modbus slave device. Yeah. So, similar to the CC-Link I-Field basic VSD, you also need to set up or parameterize your VSD to communicate via Modbus TCP. And the main difference between this and the CC-Link one is that your Ethernet function selection for Modbus is 502, and you do not set the CC-Link selection as 18, you just leave it as default 0. Set up your IP address of your VSD, the subnet mask, and then last but not least, your Ethernet command source selection IP address. So this would be the IP of the master with which the slave needs to communicate. Once again, these parameters are only those required to for the VSD to communicate for this communication protocol. You are still required to do parameterization according to your application. And once again, you also have your additional parameters, which can make a difference or can be related to the Modbus TCP. So once again, if you want to set parameters via the GOC via Modbus TCP, you need to set parameter 77 as 2, otherwise it will not allow you to do this. You'll most likely need to set the network number, but this is once again only when you are using more than one network. Station number, make sure your station number is unique, and there's no duplicates on your network. So now where we had link IO for CC Link IO Field Basic, Modbus uses registers. So it never transfers just bits, it actually transfers complete registers, where some of these registers have functions per bit. Specifically, this applies to your inverter status or control input command, both the normal and the extended one. So these are your Modbus registers for the E800 Ethernet VSD. So this is the EPB specifically. And this is what you'll use to monitor and control your VSD via Modbus TCP. So just to expand on the inverter status and control input command, because this is quite an important one. This is where you have your stop command, your forward reverse rotation command, your run high, middle, or low, and your reset. Oh, not your reset. Yeah, some other things. And this is also the register that you use to monitor. So when you are reading, the inverter status side of things applies. So this will show you whether your inverter is running or your VSD is running, whether it's running forward reverse, whether it's up to frequency, and whether there is a fault. Now, unlike CC Link iField Basic, there is not a set amount of data being transferred between the GOC and the VSD. This is more user defined. So the user chooses what registers to read and write with this communication protocol. And this is done by configuring what information you want to transfer in codices. So to do this, you still within the TCP slave window, so specifically where we set up the slave IP address. When you go to the Modbus slave channel tab, you are able to add communication channels. So this is basically instructions or requests to read or write registers, or yeah, Modbus registers. So to add a register or channel, you select add channel at the bottom. You can give it a name, select what function code you want to execute. So whether you want to read or write, or whether you want to do it with holding registers or coils or what have you. And this is also where you set the offset. So your offset will be specific to what Modbus register you want to read or write. And if you chose a function code where you are able to read or write multiple registers, you can set the length right here or here. So that is how you tell the how you set up the what communicate. Apologies. That's how you set up what data to be transferred between your GOC and VSD. So for this, we'll once again be starting off with your start and stop, reverse or forward commands. So we'll mostly be mirroring what was done for the CC Link iField basic control, but we'll just be applying it to how it would look within or for the Modbus TCP protocol. So starting off, So I've also set up variables for the Modbus TCP side of things already. And this will be specific to how we configure the channels, these variables. So that some of them might change, and I'll explain to you later on. But I've once again set up variables specific for my HMI interactions, which this case we'll be using as we did for this, for the CC link side of things. So we'll once again be starting with the start input for the HMI button. And the stop to. So once again, you need to have your start forward, also forward rotation or reverse rotation commands. One of them needs to be active for the VSD to start running. So we'll once again be using a rotation or direction selector, so the forward or reverse rotation selection bit to indicate what direction we want the VSD to run in. And once again, when this bit is 0, this will be forward. So in the case that this is true, we want to turn on our forward rotation bit. But right now I actually don't have it configured, so I don't have my Modbus slave configured to transfer this data. So let's start off by selecting or adding the data transfer. So let's give this communication channel a name so that we know what it is. And this is the control input command register that we will be writing to the VSDs. So we'd write a single register. You have an option of either having this communication done cyclically, so on a fixed interval, or at the rising edge as well. So that's user input select, and this will be communication will be executed on this rising edge. So for this instance, we will be using the cyclic communication and then offset. So going back to my Modbus registers, the inverter or control input command is what we are trying to write. And this is Modbus register 40,009. So the starting register is 40,001. So we would like to set an offset of 8 so that this is the register that we will be writing. So I'll just set it as 1. And that, apologies. That needs to be 8, sorry. Yeah, 8. Okay, so now the offset is set to 8, so this should now write to 40,009 of the VSD, so the Modbus register. Now, once you've added a slave communication channel, the register or the data transferred, the variables automatically generated for this will show up in the slave IO mapping tab. And here you can see this is the control input command, and you can see what address this is. And you can also look at the individual addresses of the bits. Now, something important to note, if you wish to do so, you are able to give labels to these bits or these variables or these addresses right here in the screen. But one thing to keep in mind, if I have named a bit, I cannot name or give a name to the entire word in the screen. So for simplicity's sake, I did go and declare my label names or variable names within the variable declaration area of my Modbus TCP control POU, which if what we just set it up as Q output bit 32, so just to make sure, bit 0 needs to be output bit 32 as our stop command. So stop command is bit 0, forward rotation command is bit 1, reverse rotation command is bit 2. So let's just ensure that my addresses are correct. So bit 0 is 32.0, 32.1, and 32.2. That's what my stop, forward, and reverse needs to be. So stop is 32.0, forward 32.1, and reverse is 32.2. So this means that I can now browse in those variables and use it in my program, because now stop command. Oh no, this needs to be forward rotation command, apologies. And now to add the reverse rotation, we'll do similarly to what we did for the CC-Link iField Basic, and just use a normally open contact and turn on the reverse rotation command, which is this one. Once again, similar to the CC-Link iField Basic, the HMI buttons will be identical, so we want them toggled. So I'll have to reset them within the program when the other is selected. So I'll once again be using the always on just so I can keep it within one network. And then for the instance where my start button turns on, I would like to reset my stop, and then vice versa. Okay. Now, one thing to note, if you notice, the Modbus TCP actually gives you a specific bit for stop command, whereas for CC-Link iField Basic, when neither your rotation nor your forward rotation nor your reverse rotation bits were active, it activated or had, okay, when neither your forward rotation command bit or your reverse rotation command bit was active, the VSD was in stop. So that acted as the stop command. Whereas for your Modbus TCP, you already have a bit dedicated to a stop command. So it's not the absence of the true states of those two bits that are required for the VSD to stop. So activating this will that bit will stop the VSD regardless of the state of your forward rotation command or your reverse rotation command. So for this, we'll be changing up this slightly. So this will be the command bit for the communication itself, and that will be activated via the HMI input. So slight difference there. So I want the communication bit to turn on, so the stop command bit to turn on when my HMI button is pressed or toggled on. So that's just the slight difference between the CC-Link iField Basic setup as compared to of the Modbus TCP setup as compared to the CC-Link iField Basic. So now, once again, you are able to start, stop, forward or reverse, and your VSD. And if it goes into fault, we need to be able to reset it as well. Now, for your reset, the reset bit or reset command is not within the inverter or the control input command register, so it doesn't form part of register 40,009. Instead, this is register 40,002. Now, how this works is when any value is written to this register, the VSD will reset. So this also means we can't set up cyclic communication to reset the VSD, because anytime that communication is executed, the VSD will reset. So you'll have to specifically trigger this. Now, to do this, we'll first have to start by adding this communication channel. So we need to tell the GOC to transfer this data or request this data from VSD. So for this, we want to write a single register, and we require it to be on rising edge so that it doesn't happen on a fixed interval. The offset for this will be 1 because this we want to write to Modbus register 40,002. Okay, so when I add that, you can see now this channel is added to my list. And when I go to the mapping, you will now actually see two things. You will see the register value, so reset, VSD reset, which is output word 36. And you will also see a trigger variable. So you'll see it described as a trigger variable. This is the variable that needs to be triggered for the communication to be executed. So when this bit turns on, the value stored within this register is written to the VSD. So just to check my variables, let's check my reset command. So this would be the trigger variable specifically is output bit 34. So let's just see if that is the same. Okay, so my trigger variable is correct in this case. And then okay, yeah, that's it. So merely writing this register to the VSD will reset it. So that actually means I don't need to set any value within this register for it to work. So it's quite frankly, we are just going to be activating this specific bit. So the ladder program for this will look as follows. When my HMI button activates or turns on, is pressed, I would like time to elapse. Well, firstly, I would like this bit to turn on. So that is my reset command. And then I want time to elapse to turn off the reset command. So similarly to the CC-Link iField Basic, we also want this bit to stay on for a bit before turning off to ensure that the VSD does reset. So this can also be made to be 50 milliseconds. And we don't require the output. So when this turns on, we would like to reset this. So using a reset coil, we'll reset the HMI input button state. Like that. And that's what you, that's all the programming needed to do the reset command or write the reset command to the VSD. So once again, for the VSD to actually start running, we will also be required to give it a speed reference. Whether this is setting a frequency or activating one of the run, high, medium, or low, or middle, or low bits, you need to give it a speed reference. For this demonstration, we'll once again be doing the setting of a frequency, which for this case, you also once again have two options. But the difference for the Modbus TCP protocol is that your first option is to write it to the RAM. So you write the running frequency to the RAM. And the second is to write your running frequency to your EEPROM. Whereas for your CC-Link iField Basic, you could write, the second option was to write it to both RAM and EEPROM. For this, we'll be using the RAM option once again, which means we will be using Modbus register 40,014 to write or set our running frequency. Now, for the Modbus protocol, you don't need any extra bits to activate it, to tell it to run at this frequency. When you write this, it will run at this frequency, provided that your run high, medium, or low bits are not on. Because your run high, middle, or low bits, or medium or low bits, will always take priority above your set frequency. So yeah, make sure that those bits are not on when you're trying to run it off of a set frequency outside of those presets. So we start off by adding this to our communication. So this is our set frequency. Yeah. And this can happen cyclically. This is not, this does not need to be triggered separately. We want it to set as write as single register, and our offset is 13 because this is Modbus register 40,014. Now, one thing you might notice when I click OK, you can actually see the offset that I have set up in this table, and you'll see it change to D. This because this displays hexadecimally, And when I go back and you'll also see D. However, you are not required to enter this in a hexadecimal number. You can just do this in decimal. It will automatically convert it as it just did. So now that we've added the communication channel, we can go look at the mapping. So the mapping for this, the set frequency uses the address output word 38. So if I just check, I'm pretty sure this does not match up. Okay, so having corrected this, we can now set up the ladder program for setting the frequency. Similar to what we did for the CC-Link I-Field Basic, the frequency value needs to be scaled once again, and also by 100, because the values, if you want your VSD to run at 50 Hertz, you need to set 50 or 5000 within this register. So we'll just be doing the same we did for the CC-Link I-Field Basic, where we will first scale, then convert from a real to a word to allow for decimals, and then ultimately that is written to the VSD. So yeah. So just start off, just use A. Okay. So starting off, we'll multiply by 100 so that our decimals aren't lost within the real to word conversion. So using the HMI input, where the user sets the frequency, multiply by 100, and store it in the temporary variable that is set up. Sorry. So once it is multiplied, it can be converted to a word. So we want to convert this one to word, and the converted value needs to be stored in what is going to be written to the VSD, which in this case is the custom frequency. So that is Q, or output word 38. And that will allow your that will write your frequency value to your VSD. So it's not necessary to limit this to only happen when a button is pressed, because this is the only frequency we are setting. So last but not least, monitoring the VSD output frequency. Works slightly different than the CC-Link I-Field Basic. As each value that can be monitored with the Modbus TCP protocol is assigned its own specific register. The table which indicates this, sorry, is here. So to monitor the output frequency or the speed of the VSD, you need to read Modbus register 40,201. So that is the register that we want to read. So that's the communication we need to set up, or I need to set up in the slave channel. So if I go to this and I need to add my slave channel to monitor my output frequency. So we want to read holding registers. This can happen cyclically, and offset. So offset will be 200 because starting register is 40,001. We only want to read this one register, and when there is an error, I want this value to go to 0 to indicate that there might be an error. So that is how you set up the channel, communication channel, and the mapping, IO mapping that will be generated will now actually be in the input word range. So this is being read from the VSD, so this will be of address input, so IW32, which if I look at my variables I've set up, it is already set up as such. So I don't need to add ladder programming to actually do the communication and read, tell the VSD to read that value. That is done via that communication channel we just set up. All we have to do, or all that has to be done for display purposes, is scaling the value back to normal. So once again, when we read the frequency, it will be multiplied by 100. So to display it appropriately, you will be required to divide it by 100 to display it accurately. To do this, we'll be doing the reverse of what we did for the output frequency, where this will be firstly scale, sorry, wrong direction. We'll first be converting it from a word to real, in order not to lose the decimal points, after which it will then be scaled, so divided by 100. So taking this value and now displaying it in the variable that I want to monitor in my HMI program. So that scales the value back down to its appropriate value for display. Now that is actually all the functionality that we added to the CC-Link 1 as well. So we can now move on to setting up the HMI screen controls, and I'll actually just be copying and pasting what we did previously and changing the variables for this. So start push button set up for my second VSD, and then once again the color variable also. So that I'll be changing each of the variables for the controls for VSD2, after which I can demonstrate to you how it works, or just show you that it works. So this would be our stop HMI push button, and I'll copy and paste this. So this controls the color and the input configuration that you change. Determines whether this is the where you set the variable to be toggled. So it's the action taken when the button is pressed, which we want this to be the stop button. And this is the start button, and then yeah, the same is changed for each of these buttons, just to the appropriate HMI button for the second VSD. So for these frequency set, the variable that needs to be set is what variable is displayed, which in this case for our second VSD is this one. And then you also need to change the variable that is written also to that specific one that is set up for the second VSD. And last but not least, for monitoring, it is just the text variable that needs to be changed to the correct one. Now, to test. So my compilation shows no errors, so I am able to download to my GOC to run this program and hopefully control my VSD. Okay. It's just about finished downloading, so setting it to run, and let's monitor the Modbus ladder. So you can see it's currently stopped. And looking at this piece of ladder, if I set my frequency, let's say to 35, you can now see the variable being scaled to 3500 so that it can be written to the VSD. And when I press start, actually I need to reset my VSD first. And when I press start, you'll see the value of the output frequency increasing, and you might even hear the motor connected to my VSD start to run. If I toggle the direction, as you see, it's currently running forward. When I toggle my direction, you can see the speed decreasing and will eventually start ramping up as it's going in the other direction. If I change the frequency that I've set, let's say change it to 40, you'd see it ramp up to 40. And if I ultimately press stop, you'll see the VSD's output frequency ramp down and ultimately stop at 0. Okay, and that is actually all the functionality that I'm going to show you today. Obviously, there's quite a bit more you can do with your VSD over communication protocol, but this is some of the very basics that can be done. That being said, that is the end of today's technical session. Sorry, it was a bit of a longer one, but yeah, there was a lot of information to cover. Are there any questions regarding today's session or presentation?